Hey everyone, so this video is going to be on acids and bases and how to calculate pH and all this fun stuff. But first let's define acids and bases. So there's several different definitions that we can use to describe an acid or a base. You need to be familiar with them. So one of them is the most common definition of acids and bases, probably what you already think of as being an acid or a base. It's what the middle school uses as definitions, and that is the type 1, where it is Arrhenius acids and bases. So an Arrhenius acid is a substance that will produce hydrogen ions in solution, or H plus ions. Okay. An Arrhenius base is a substance that produces hydroxide ion solution, hydroxide ions in solution, or OH minus ions. And we know that you should know that when you react an acid with a base, you always get some sort of you get water and some sort of salt. Now, salt is not always NaCl. Salt is just a classification of a type of compound. It's an ionic compound. Anything that comes from the ions in the acid and the base. Now this reaction shown here is called a neutralization reaction. Alright, and so we are going to do a couple examples of neutralization reactions and look at what the salt is that is formed. All right, so this first one we have, we have sodium hydroxide reacting with hydrochloric acid. Well, sodium hydroxide, sodium is Na plus 1, hydroxide's OH minus, so that's NaOH, and it is reacting with hydrochloric acid. Well, hydroic comes from just the ion, and the oxygen's not a polyatomic ion, so that's HCl. And they're going to react together. This is a double replacement type of reaction, so Na and H are going to switch places. So Na is going to be with Cl, and hydrogen is going to be with OH. Oh, HOH, that's the same. Oh, my hand hit the next thingy. Sorry about that. HOH, that's the same as water, so that's H2O. This is my salt. This is my acid. And this is my base. All right, let's do another example where NaCl is not the salt that is formed. All right, this one, phosphoric acid reacts with calcium hydroxide. Well, phosphoric comes from phosphate, so hydrogen phosphate. Phosphate is PO4 minus 3, so H3PO4 reacts with calcium hydroxide. Calcium has a +2 charge. All right. Again, another double replacement type reaction. Hydrogen and calcium are going to switch places. So calcium is now going to be with phosphate. Calcium is +2. Phosphate is -3. So Ca3PO4 2 plus HOH or H2O. All right. And if you were to balance it, you would need a 3 in front of this, and then a 2 in front of this, and a 6 in front of the water. But again, this is just another neutralization reaction where phosphoric acid is obviously my acid, calcium hydroxide is my base, H2O is obviously water, and this guy here is my salt. See how it's different than NaCl? It's just an ionic compound, and that's what classifies it as being a salt. All right, the second definition for acids and bases, is Bronsted-Lowry acids and bases. So Bronsted-Lowry, a Bronsted-Lowry acid is something that is a proton donor, and a base is something that is a proton acceptor. And what they mean by proton is the hydrogen ion, because the hydrogen atom only has one proton and one electron, and most of them have no neutrons. So if you ionize it, if you make it an ion, the hydrogen atom, if you make it an ion, it likes to form the +1 ion, so it'll lose its one electron, and therefore it'll just be H+, and it'll just be one little proton. So proton equals H+ ion, okay? So that's all that means. So instead of looking at what each one gives off in solution, we're looking at what's happening to the hydrogen ion. So an acid gives off a hydrogen ion. That's the same definition as Arrhenius acid. But the base, instead of giving off OH minus, is giving off, or is accepting that hydrogen ion that the acid gave up. So if you look in this example, this is just a general formula. This guy's my acid. This is my base. So the hydrogen is going to jump from the acid to the base, leaving behind A minus, and now this base has an extra hydrogen, so it becomes positive. All right, type 3, we really aren't going to do many examples with this, but just kind of know the definitions that an acid is an electron pair acceptor, a base is an electron pair donor. This is more for organic stuff, which only if you take organic in college will you have to worry about that. They don't even really go into that much with AP. They recently took that off the AP stuff, but I just like you to know, hey, there is organic chemistry is completely different, and it does a completely different thing in terms of acids and bases. All right, so let's look back to the Bronsted-Lowry stuff. So you need to know Arrhenius and Bronsted-Lowry. That's the main ones. So when the Bronsted-Lowry acid gives off its hydrogen ion to the base, they both create these conjugate acids and bases as the products. So a conjugate acid is what came from the base accepting that hydrogen ion. And the conjugate base is what was produced after the acid gave up the hydrogen ion. So for example, acetic acid, which comes from acetate, which is C2H3O2-, so HC2H3O2, reacts with water. Well, acetic acid is obviously my acid, so therefore water is going to be acting as my base. Water can do that because it is amphoteric. It means it can act as both an acid or a base. Okay? So when these react together, and this actually gets that special equilibrium arrow, when these react together, the acid donates its hydrogen to the base, so this hydrogen on the acetic acid is going to be donated to the water, and we're going to produce H3O+, because it gained a hydrogen, and gained an H+, so the charge goes up by 1, and C2H3O2-. So now this, the H3O+, this is the substance that remains after the base accepted a hydrogen ion. So that is my conjugate acid. And acetate is my conjugate base. Alright, so now let's look at how we can do some calculations with this stuff. Oh, nope, sorry. I forgot that I need to tell you what strong acids and strong bases were first. So, in terms of acid strength, a strong acid or base, so something that is strong, will completely dissociate. And it acts like an ionic compound. Way back when I taught you naming rules, I said for acids, just treat it like an ionic compound and name it that way and then change the name. And I said, acids are weird. Some of them act like ionic, some of them act like covalent. And it all depends on the strength that it has. So a strong acid will completely dissociate in water. All right? And the same thing with a strong base. Something that is weak will not completely dissociate in water. So the 6 strong acids, you need to know what these 6 are. We've got HNO3, which is nitric acid, HCl, which is hydrochloric acid, HBr, hydrobromic, HI, hydroiodic, H2SO4, sulfuric, and HClO4, perchloric. Those are the 6 strong acids that you need to worry about. P.S. There are more, but only if you go on to AP. Now, strong bases are any compound that contains a group 1 or group 2 metal with OH minus. So group 1 is going to be like sodium, lithium, potassium. Group 2 is going to be like barium, strontium, magnesium, calcium, those guys, okay? If it's any other base, and it's not one of those, like if the metal in the base isn't one of those 2 groups, it's not strong. So like aluminum hydroxide, not a strong base. Now with the acids, if it's not one of those 6, for your purposes, it's not a strong acid and therefore it is weak. Like H3PO4, not a strong acid, it's going to be weak. HF, not a strong acid, it's going to be weak. Okay? So now, let's get into how we can do some calculations with pH and stuff like that. You've heard of pH before, back in like 8th grade. You might have seen this nice little pH scale. So when you have a low pH up here, low pH, so you have a low number, we're more acidic. This got, up here we're acidic. We've got a high hydrogen ion concentration. Down here, we've got a high pH, but we're more basic. All right, 7 is neutral. And then there's some examples. So pH is a measurement of the hydrogen ion. And it's a log-based scale because the numbers, the concentration of hydrogen ion gets really, really, really tiny as you get more and more basic. So it's easier just to put it in this log-based scale. There is a scale called pOH, which is a measurement of the hydroxide ion concentration. pH and pOH are kind of like opposites. A high pH is more basic. A low pOH would be more basic. All right. So just know that, hey, that other scale exists. When we do some of our calculations, we will calculate pOH as well. All right. So here are the formulas for how we can calculate acids and bases. And actually, before you write any of this down, it's better if you go by this chart. So this kind of shows the 4 things we'll be calculating. We'll be calculating H plus concentration. Remember, those brackets mean concentration in molarity. We'll be calculating the hydroxide ion concentration. We'll be calculating the pH. And we'll be calculating the pOH. So these things will tell us how acidic or basic a solution or a substance is. So if you have the H plus ion concentration and you want to find the OH minus ion concentration, you're going to use the KW formula. KW is the equilibrium expression for the dissociation of water. Water dissociates in H plus and OH minus, and only those go in the equilibrium expression because water is a liquid. KW, it's constant, so it's always the same, and it's always that number. Yeah, you need to memorize it. You need to memorize this entire chart. Okay? But KW is always that number, 1.0 times 10 to the negative 14. So if we have one concentration, we can divide to find the other. If you want to find pH and you have the hydrogen ion concentration, you're going to do pH equals negative log of the H plus ion concentration. So everyone look at your calculator real quick. If you find the 7 button, if you're using a TI series, if you're not, then good luck. If you find the 7 key, the button next to that, that's your log button. So that's the one we're going to be using. So we're going to hit negative log and then type in whatever the concentration is. And that will get you your pH. Say you want to go backwards though. Say you have pH and you want to find hydrogen ion concentration. The opposite function of log, the second function, is 10 to the x. So you're going to type in second log, that'll bring up 10 to the x, and then negative whatever your pH is. And that will get you back to the hydrogen ion concentration. If we have a hydroxide and we want to go to POH, it's the same thing as finding pH, because if you do the negative log of the OH minus concentration, then that gets you POH. And again, if you want to go backwards, you're going to do 10 to the negative POH. And then say we have pH and we want to find POH, or vice versa. That's real easy. They both add up to 14. The pH and the POH of the same substance always adds up to 14, which ironically is the same as the exponent, only with a negative sign in the KW formula. It's like that for a reason. It's math. So if you have pH, you can subtract that from 14 to find POH, or vice versa. All right, so now we're going to do some examples. You have this one in your packet. So we are going to find we're going to find all four of these things. We're going to find H plus, OH minus, pH, and POH. So find H plus ion concentration. That one's probably one of the easiest ones because we have HBr, and we know this is a strong acid, so there's 100% ionization. It completely dissociates. So the concentration of the HBr is equal to the concentration of H plus because they're stoichiometrically equal. So that means that the H plus ion concentration is 0.015 molar. Sweet, that one's done. Now to find OH minus, if we look back at our little chart here, we have H plus, we want to find OH minus, so we're going to use KW. So we know that KW equals H plus times OH minus. So that means we're going to do 1.0 times 10 to the negative 14 over the H plus concentration, which is 0.015. And remember, KW never has units, but concentration always, at least these brackets are always in molarity, so our OH minus concentration is going to be in molarity. So if I do 1.0 times 10 to the negative 14 divided by 0.015, I get, and with proper sig figs, which are going based off of our concentration, 6.7, did it again, times 10 to the negative 13 molar. And that's my hydroxide ion concentration. All right, now to find pH. pH is equal to negative log of H plus. Well, I found H plus in A, so I'm going to do negative log of 0.015. So, negative log of 0.015. I get 1.82. Now, you're probably wondering what the sig figs are with that. So, the sig figs for logs is the number of decimal places after, or the number of digits after the decimal, that equals your sig figs. So whatever comes before the decimal doesn't matter for sig figs. So since we had to have 2 sig figs in our answer, because our concentration had 2 sig figs, we need to have 2 decimal places, or 2 numbers after the decimal place. All right, now to find POH, we could do a couple different things. We could do negative log of my OH minus concentration, which I found right here. Or we could just do 14 minus the pH, which I found right here. You will find that no matter which way you do it, you're going to get the same answer. So I'm going to do 14 minus pH for this one. With the next example, I'll do it the other way. So you should get POH being 12.18. All right, so we're going to do one more example, and I changed the example that's in your packet, so please correct it to be this. Instead of whatever it was, I want it to be 0.00500 molar KOH. Right? I think I kept the concentration the same, but the substance is different. I wanted it to be a base. Right? And that's because one of your homework problems is a base, and I want you to know how to handle that one. So, we're going to find these 4 things again, but this time we can't find H plus yet because this is the base. It has OH minus. So that means we got to find OH minus concentration first. But since this is a strong base, we have a 100% ionization. So that means that the OH minus concentration equals the concentration of KOH. Real simple, right? So that means OH minus equals 0.00500 molar. Then to find H plus concentration, if we look back at our chart, again, we have OH minus, we're going back to H plus, so we're going to use KW. So we're going to take 1.0 times 10 to the negative 14 and divide it by, oh, I just messed up my 14, divide it by 0.00500. And we're using 1.0 times 10 to the negative 14 because it is KW. It's a constant. It's always the same. You must memorize it. Yay. And so you get 2.00, because of sig figs, times 10 to the negative 12 molar. And that's my H plus concentration. Now to find pH and pOH, we could do negative log of both of the things we have. So pH will be negative log of, nope, not 2.00 times 10 to the negative 12. Now we have 3 sig figs, so that means we have to have 3 numbers after the decimal. So you get 11.699. High pH means it's basic, which makes sense because KOH is a base. And then for pOH, we're going to do negative log of 0.00500. Well, we have 3 sig figs, so we need 3 numbers after the decimal. So we get 2.301. And if you notice, the pH and the pOH always add up to 14. So now, that's it for acid and base calculations. We're going to do a little bit more with this on Thursday and Friday when I return. But I want you now to work on the worksheet, which is finding these 4 things just like we did with these 2 examples. So very straightforward. And then after that, work on your SLO review packet. All right, I'll see you later this week.